Hello everyone, welcome to Easy Physics once again. Now we are going to look at the refraction through parallel plates and prisms. See, we have a glass plate and a ray is incident from air to the glass. Here is the normal, and the incident ray is making 45 degrees with the normal. Once it is refracted, it will make 28 degrees with the normal. There is some reflection from this surface, but we are not interested in the reflected ray. Now concentrate on the refracted ray, and it is making 28 degrees with the normal. And this refracted ray is now going to be an incident ray for this boundary. And this incident angle also going to be equal to 28. Why? Because this line perpendicular and this line is also perpendicular to the boundaries. They are the normal. That's why 28 and 28 degrees will be equal to each other. Now, moving from glass to air like this is same as moving from glass to the air like this. Both will be the same. That's why this angle also going to be equal to 45 degrees. Let's look at the prisms, refraction through the prisms. See, there is an incident ray toward the prism and how it is going to be refracted. Let's first draw the normal at this point. This is the 90 degree to the surface, and the incident ray is going to move away from, it is going to move toward the normal. Why? Because it is from air to the glass, where glass has a higher index of refraction. That's why originally this light ray was moving toward that direction, but it has bent toward the normal a little bit, and then it has refracted like this. This is the angle of refraction. Then what? Now the angle, this incident ray is now coming to this surface. Let's draw once more the normal for this point. Okay, so when moving from glass, I mean the prism, to the air, it must move away from the normal. This was our original light. It was moving toward that direction. This is the original direction of the light. But now it must move away from the normal. Here is the normal. This is the normal. So it is going to move away from the normal, and this is the refracted ray from the prism to the air. Now, amount of deflection. This was the original light ray before entering the prism, and now this is the transmitted ray, and this is the amount of deflection. Okay, let's solve some examples related to the transmission of light through glasses and plates. Now here we have a prism, and this is the incident ray. Just like the previous one, I'm going to draw the normal here. This is the normal, and the original light is refracting toward the normal. It means that the index of refraction of this material of the prism is bigger than the index of refraction of the medium on the left. I mean the medium K has lower index of refraction when compared to the medium L, since the light ray, when it enters this medium, which is a prism, it is bending toward the normal. See, this is our normal. So then we are going to write that NL is bigger than NK. Now let's look at the refraction of the light at this boundary. Again, let's draw our normal perpendicular to this surface. Okay, this is the incident ray to this point, and this is the original direction. As you see, this light ray has bent toward the normal. This is our normal. It has bent toward the normal. That's why it means that this index of refraction of M is bigger than that of L. And we are going to write that index of refraction of M is bigger than that of L, and it is bigger than that of K. Let's move to the next question. Here, a light ray is incident on a prism, and this is 90 degree. That's why it will not deflect, and it will not refract, and it will come to this surface. So from this surface, let's write Snell's law for this surface. Initially, I need to draw the normal again. Okay, so this is 90 degree, this is 30 degree. It means this will be 60 degrees. Okay, so here is the 90 degree again. This normal is making 90 degree with the surface. What will be this angle? The angle of incidence. This light ray is making how many degrees with the normal? See, this was 60 degrees, and since total should be 90 degree, this will be 30 degree. The angle of incidence is 30 degree. Let's write the Snell's law. We know that n1 sine theta 1 equals n2 sine theta 2. It is moving. Now I'm going to write the Snell's law for this boundary between the glass and the air. It is moving from glass to the air. So then index of refraction of the glass, let's say it is n1. I don't know, we don't know if it is glass or not, sorry. Just we are going to find the index of refraction of the prism. n1 times sine 30, because angle of incidence is 30 degrees. And what is the angle of refraction? By the way, it is moving to the air, that's why in n2 is 1, it is index of refraction of air. And let's look at the refracted angle of refraction. It is the angle the light ray is making with the normal. As you see, this is the incident ray and it is moving toward that direction. So what is the total angle with the normal? This is the total angle with the normal. Here is 22.6 degrees, and this angle is going to be equal to that angle, which is 30 degrees. Why? Because they are opposite angles. This is also going to be the 30 degrees. So I'm going to write sine of 30 plus 22 is 52.6 degrees. Okay, now we are going to calculate n1, which is the index of refraction of the prism. What is in the sine of 52.6 degrees? If you go to some sources, you are going to see that the index, the sine of 52.6 is 0.794. Divide by sine of 30, it is 0.5, and if you do some calculations, you are going to approximately get 1.59. Let's look at the next example. A laser beam is aimed at a 1 centimeter thick sheet of glass at an angle of 30 degrees above the glass. The index of refraction of the glass is 1.5. By what distance is the laser beam displaced? We are going to calculate the amount of displacement as I described in this figure. So let's move to our question. Here, let's draw first a glass sheet. This is a glass sheet, and a light ray is going to be incident on this glass sheet. This is the incident light ray. I'm going to draw the normal at this point, and this incident ray is going to refract toward the normal. Let's draw the normal for this point. Once more, the light is going to refract when it passes to the air. When it passes to the air, it will refract once more. This is the angle of incidence. It is given 30 degrees. This is theta 2. This will be also equal to theta 2. And from our previous explanations, this is also going to be equal to 30 degrees. Now we are going to calculate the amount of deflection. Originally, the light ray was moving toward that direction. Okay, so this is the amount of deflection. How much the light is deflected? The amount of deflection will be equal to the length of this line, and it is perpendicular to this one, and it's also perpendicular to this parallel light rays. Let's call this one D, and the thickness of the sheet is given as T, equal to 1 centimeter. So first we need to calculate theta 2, and then we are going to use it in our calculations. Let's use Snell's law. N1 sine theta 1 equals N2 sine theta 2. N1 is index of refraction of air. Sine theta 1 is the sine of 30, it is 0.5, equals N2 is the index of refraction of the glass, it is 1.5 times sine theta 2. From here, sine theta 2 equals 0.5 divided by 1.5, and it is going to be equal to 1 over 3. Then we can look at it, and we can look at which angle has this sign. If you look at some sources, you can see that it is approximately 19 degrees. Here we have 19 degrees. So let's calculate the amount of deflection. To calculate the amount of deflection, I am going to use some triangles here. here we have a triangle. Okay, this triangle, please look at this triangle. In this triangle, this is theta 2 and it is 19 degrees, and this side is it has a length of t, and then let's call this length, this refracted ray, its length, let's call it to be L. Assume this is L. And how can we write for the cosine of theta 2 will be equal to t over L. The cosine of this angle is this side divided by that side. From here we can write that L will be equal to t over cosine 19. And we know that t is equal to 1, it is given in the problem, divided by cosine 19, you can find it as 0.94, and once you divide them, you are going to get approximately 1.06. Now we know this length, and now let's use this triangle. In this triangle, what is the amount of this angle? As you see, let's call it theta 4, since this can be theta 3. So theta 4 is going to be equal to theta 1, which is 30 degrees. 30 minus theta 2, it is 19 degrees. So it will be 11 degrees. This angle will be equal to the 11 degrees. Why? Because see this line, okay, and also see this line. This angle, I mean theta 2 plus theta 4, they are going to make 30 degrees. That's why theta 4 will be equal to 30 minus 19, which is approximately equal to 11, not exactly equal to, it is exactly equal to 11 degrees. So let's use this triangle. And what is sine of theta 4? Sine theta 4, I mean sine equal sine 11, will be equal to, and the sine of this angle is d over L. It will be d over L. If you use your calculator, you are going to see that sine 11 is equal to approximately 0.19. So from here, d will be equal to L times sine of 11. It will be equal to, L was 106 times 0.19, and this calculation is going to give you approximately 0.2. Thank you for listening.